Alright, this is lecture 5 over chapter 5 in your book. Okay, we're going to start talking about parallel circuits. So last chapter we talked about series circuits, and now we're going to talk about parallel circuits, and we're going to be able to see what the difference is between the two and learn how to do all the basic calculations for a parallel circuit. And then next chapter we're going to put series and parallel circuits together. So we're going to talk about resistors in parallel, current, what happens to current in parallel circuits, what happens to voltage in parallel circuits. We're going to apply Ohm's law again. Remember, it's fundamental. And we're going to talk about KCL, Kirchhoff's current law, and we're going to briefly touch on current dividers, and obviously we are going to calculate power. Power is very, very important as we go through this. So, resistors in parallel, okay, they are connected between 2 points, okay? So each one of those black dots that you see on there, above R1, R2, R3, all right, and below R1, R2, R3, those are called nodes. That means all 4 of those resistors connect at the same point, and we use a node junction to represent that. All right, so that's a node, and this is what they're going to look like when they're in parallel. Think of like 2 people getting married and holding each other's hands. That means that that's a parallel connection. So if we relate this to Christmas lights, if I pull out R3, the light R1, R2, and R4 will be on. They're not lights, they're resistors, but in our essence, when you buy lights that are wired in parallel, all right, the one that goes out's the only one that goes off and stays off, while the others can still remain on, just like in your house. So when one light bulb goes bad in your house, all right, the entire light bulbs on the same circuit don't go out. So like your kitchen lights, you know, one light bulb goes out, they don't all go out. They're connected in parallel. We run one wire, but it's how we physically connect them, all right, at their connection points so that they're running in parallel. So R1, R2, R3, R4, they're all connected to the same location on each side. They're all sharing the same signal. So that's very important. And we're going to do some breadboarding and troubleshooting on some circuits and things like that, where we can get a better idea of that and what it looks like. All right, so what we define a parallel circuit by, same picture here, so if you need to pause the video and go right ahead and draw the circuit down. But what's different, all right, in parallel circuits is we have what we call branch currents, which means the current will go through each branch of the resistor. So there's a current I1 that goes through R1, there's a current I2 that goes through R2, there's a current I3 that goes through R3, and there's a current I4 that goes through R4. Are each one of those currents the same? Not necessarily. Can they be? Yes, if all those resistor values are the same. If the resistor values are not the same, the branch currents will each be different. Alright, does that make sense? So if the resistor values aren't the same, the currents won't be the same. But if the resistor values are all the same, the currents will be. So in a parallel circuit, you will have multiple different currents, all right, and the currents will vary. Versus the series circuit we talked about last chapter, there was only one current and one path. A parallel circuit has multiple currents and multiple paths, multiple being more than one path in general. So 2, 3, this one, you know, has 1, 2, 3, 4 different paths that it can take. And there still is an I total as well when we're talking about current. Okay, so the rule for voltage in parallel circuits, all right, is the voltage drop across each component that is parallel connected is the same. So the voltage drop across R1 is 5 volts. The voltage drop across R2 is 5 volts, and the voltage drop across R3 is 5 volts. So when circuits are in parallel, or resistors are all in parallel, or whatever component is all in parallel, the voltage across them will all be the same. So 5 volts, 5 volts, 5 volts. That's important for us because that will help us find all the branch currents, because now we know a voltage and a resistance. We can just apply Ohm's law and find each one of those branch currents. All right, so very important for us. We're going to get to this. We're going to solve this entire circuit towards the end of the lecture here. So you'll be able to see that. But if we were to take a meter, all right, a multimeter, turn it to voltage. Obviously, we're reading 5 volts DC here. So we got to be on DC voltage on our meter. And we put it across each terminal, okay? As the circuit is turned on, Every single reading should say 5 volts. All right, so when we're talking parallel circuits, current has multiple paths. Okay, more than one path, and please remember, we can call them paths, or we really call them branches. So we can interchange both of those. Where a series circuit, like the one on the left here, there was one path for current, all right, and then we had voltage drops in a series circuit. In a parallel path, the voltage remains the same, and we have different currents, or multiple paths for currents. It's really kind of breaking it down when we take a look at the two. So always assume, okay, that the voltage is going to be constant there. Now, how do we change the current in resistance? So what's really important is if we add an additional resistor, okay, that's going to reduce the resistance and increase the total current. I know that doesn't make sense and sounds backwards. All right, so let's break it down. Let's talk about a series circuit first. A series circuit, what happened? If we added more resistance, current would go down, right? In a parallel circuit, when we add more resistors, current will go up. It's the opposite. So the more resistors in parallel, the smaller the total resistance will be. All right, and that's a way that we can solve the circuits and know if we did it right. The total resistance in a parallel circuit will always be less than the smallest resistor in parallel. I'm going to repeat that again as we do a problem so that you can see it. All right, but adding more resistors in parallel actually lowers the total resistance, all right, which increases the current. All right, we'll get through the examples and we'll brush on that more times so we can see it. So this is just to reiterate, if we look at this example, if we have a 10 ohm resistor and a 100 ohm resistor connected in parallel, the total resistance has to be less than 10 ohms. It has to be smaller than that smallest resistor in parallel. And you'll see when we start doing the calculations, all right, because we're using the inverse function when we calculate total resistance, all right? So go ahead, make sure you pause the video for a second and draw this circuit down, because we're going to do basically setting up how to calculate the total resistance for a resistor in parallel. So go ahead, pause it, write it down, and then we'll pick it up here as we take notes. So the total resistance, all right, is the reciprocal of the sum of the reciprocals of the individual resistors. Now that is wordy, right? That's confusing. We're thinking reciprocal. All right, that's a math term. All right, we're taking a reciprocal of a reciprocal. Well, remember, a reciprocal is 1 over whatever we're talking about. But now we're going to go 1 over whatever we're talking about. So I know that sounds confusing, all right, but this is really what it means here. Now, I'm not going to have you do it this way. It's kind of the old school way. You got to fumble through the algebra, get common denominators. All right, even if you're using your calculator, there's a lot more room for you to screw up with errors and parentheses and order of operations in your calculator. But this is really what it's saying here. RT, total resistance. Okay, it's the reciprocal, so 1 over, and then it says the reciprocals of the individual resistors. So the reciprocal of the individual resistors are 1 over R, 1 over R2, 1 over R3, 1 over R4. Please remember, this is the only way to calculate parallel resistance. You do not calculate it the same way that you do series resistance. I know it is tempting, and most of you, or not most of you, but some of you will do that, and you will be wrong. All right, and I did put that on your tests and quizzes to make sure that you know that you have to do this in parallel, because I put it, if you did it in series, as an answer choice. So just know that I tried to get you on those tests and quizzes that we're going to be taking. So, all right, this is how we calculate total resistance. What I want you to do is remember it this way. I'm just going to take the sum of all the resistors individually inversed. Mathematically, these two mean the same thing. That little -1 really means 1 over R1 in math terms, okay? So, to calculate the total resistance for this specific circuit, it's R1 inverse plus R2 inverse plus R3 inverse plus R4 inverse. Quantity, meaning parentheses, right? That entire thing is inversed at the end. So for you to get this right, you will use your calculator and you will plug it in exactly as you see it. Okay? That's the only way you're going to get that right. That's the most simplest way to calculate total resistance in a parallel circuit. So let's apply what we just learned. All right, this is the circuit I showed you a few minutes ago. All right, we have three resistors in parallel. We have R1, which is 680 ohms, R2, 1.5 kilo ohms or 1500 ohms, R3, which is 2.2 kilo ohms or 2200 ohms. Okay, I'm going to go back and forth between SI and its standard form just so that you are able to start going back and forth in your head, no problem when we do this. So take a second, draw the circuit down again, and then play the video again because I'm going to walk through it here. Alright, so total resistance for this specific circuit, there's three resistors in parallel. So total resistance is going to be R1 inverse plus R2 inverse plus R3 inverse, quantity or the whole thing inversed. Alright, and you can see on your calculator there's the X to the -1 button on your calculator. That's what you're doing. I think on your cell phone, if you hit calculator and turn your cell phone sideways or landscape, you should have that option. Else, if not, download one that does, or have a calculator that has an inverse button, or you got to plug it in the old school way. So now we're going to substitute in the values of the resistor. So RT is going to be 680 inverse plus 1500 inverse plus 2200 inverse, all inverse. Put it in your calculator exactly as I wrote it right there, okay, and hit enter. You don't put in the RT equals, but everything within parentheses and that to the power of -1, all right, in your calculator. When you get that in, you should be getting approximately 385.83. If you aren't getting this, double check yourself, all right, or email me or ask me in class, and I'll show you how to use your calculator if it's something where you're, hey, I just don't get this. Some of you might have a reverse Polish calculator, so if you have like an HP or some of the Casio ones, they don't necessarily go in like this, so you might have to do it a little differently or look it up. Those I'm not as familiar with. If you have a TI calculator, it's going to work just like this, no problem, all day long. All right, and then what I'd like you to do is, most likely on a test or a quiz, I'm going to have you round that up. 385.83 is really 386, and we can call it 386 because remember, and I think it was our first lecture or second lecture where we talked about resistor tolerances, okay? So there'll be some tolerances on all these, so we can approximate it to be 386. That's completely fine, all right? When you do your calculations, carry out the decimal point because you'll be more accurate. All right, why don't you pause this and find the total resistance, and then I'm going to keep going, obviously, and calculate it. But see if you can do this one on your own. You got to remember how to do parallel resistance when we do this, all right? So first one, there's three resistors, so our total is R1 inverse plus R2 inverse plus R3 inverse, quantity inverse. Substitute in the values. So we're going to have 100 inverse plus 47 inverse plus 22 inverse, all inverse. Now, before we get to the final answer, a few slides back I talked about, the total resistance in a parallel circuit has to be less than the smallest resistor in parallel. So if we look at this circuit up here, the smallest resistor in parallel is 22 ohms. Okay, 22 ohms. So our total resistance has to be less than 22 ohms. If it is not less than 22 ohms, we did something wrong in our calculation. Okay, if you're getting something less than 1 ohms too, you forgot to do the last inverse as well. But our answer needs to be less than 22 ohms. So when we put that into our calculator and get our value, we get 13.03 ohms. All right, make sure that you're getting those calculations down right. But 13 is less than 22, so we did do the total resistance in the parallel circuit correctly. Okay, the total resistance calculated has to be less than the smallest resistor in parallel. We have to be less than 22 in this case. All right, here's a shortcut. It's kind of for the old school way. I'm still all about just using the calculator and plugging and chugging and doing it that way. But sometimes just a quick shortcut If you only, this is only, and this is why I don't like showing this all the time. This is only if you have two parallel resistors. If there's three, you're not going to do it this way. All right, this is only for two parallel resistors. You can take R1 times R2 and divide it by R1 plus R2. Or you can use the other way I taught you using the calculator inverse. R1 inverse plus R2 inverse, quantity inverse. So let's say that R1 here is 27 kiloohms, R2 is 56 kiloohms. Now they're both in kiloohms. You could do the whole calculation using 27 and 56 to know your final answers in kiloohms. Or I wrote them all out here, or get some big numbers here. But RT, all right, so I took 27,000 times 56,000 and divided by 27,000 plus 56,000. So when you get, you see the numbers here. I don't want to waste time reading those off. And then you hit divide, and we roughly get, what, 18,216. Now, is that answer correct? What's it have to be less than? It has to be less than 27,000. Is it less than 27,000? Yes, most likely we did this correctly, okay? Now, and if we round or rewrite it in SI, 18.2 kiloohms is probably going to be like your answer choice or something like that on your quiz, okay? Or, just simply plug it into your calculator and hit enter. I'm okay with either one, but I can show you the shortcut for two, but do what's comfortable for you, and just remember it only works for two. That's the only thing I don't like always showing that one, because some people try to apply it to one that has four, and you can't do it that way. All right, let's step up now. We're going to do this circuit here. It's just kind of there's only two resistors in parallel now. See how they all go to ground? That's still a common node because ground is common. So you may not see the node. Above R1 there's a node, right? That black circle, that's a node where circuits junction together, okay? Since ground, they're all going to ground, we treat it just like a node because they're all going to the same connection. So these are in parallel, all right? This is more common in our book and from this author. Most of the time, you'll connect all those to one ground connection instead of showing them individually. But know that ground connection means they're all going to the exact same place, so these circuits are in parallel. All right, so we're going to find I1, that's the current going through R1. We're going to find I2, that's the current going through R2. Now we're going to find IT, which is the total current, okay? And we're going to find the total resistance. So if you want to pause and make sure you're getting the total resistance, that's fine. Pause, draw this circuit out, all right, so you can use it on your notes for your lecture quiz. What I want you to know, though, what are you asking yourself in your head? All right, I got two resistors in parallel. I know that my answer for total resistance has to be what? Smaller than 330 ohms, because 330 ohms is the smallest resistor in parallel. So I know my answer has to be less than 330 ohms. So you can either use the two methods that I showed you on the previous slide. I'm going to use this one. So RT equals R1 inverse plus R2 inverse, all quantity inverse. And remember, that's the button on your calculator. It's usually like you have to hit second and 1 over x. If you look for 1 over x on your calculator, if you hit second 1 over x, it should be like that inverse button on there. All right, substitute in the values. All right, and we should get the total resistance is roughly 222 ohms. That's less than 330. That means we did the calculation correctly. Now, here's the beauty of this to find the currents. This is a parallel circuit, which means the voltage across the parallel branches is always the same. So the voltage drop across resistor 1 is 12 volts. The voltage drop across resistor 2 is 12 volts. So I can apply Ohm's law at each resistor and find each branch current, I1 and I2. So Ohm's law for current is Vs over R1. So that's to find I1 for us. Okay, substitute in the values. We have 12 divided by 680, the specific resistor R1. Okay, Vs stands for the voltage source. The voltage source in this case is 12 volts. When we calculate that, you're going to get 0.0176, which is 17.6 milliamps. Okay, we're going to apply the same law, Ohm's law, to find I2. I2 is going to equal Vs over R2. So we're going to get 12 divided by 330, which gives us 0.03636 or 36.36 milliamps. All right, Kirchhoff's current law, and we're going to talk about it a little bit more. It's just like we had Kirchhoff's voltage law with series circuits, right? The sum of the voltage drops have to equal the total voltage source. Okay, with parallel circuits, the sum of the individual currents have to equal the total current. All right, so I've drawn on there IT. If we look at the schematic, I'm showing you where I1 and I2 are and IT. So using Kirchhoff's, or however you want to pronounce his name's current law, so KCL, the sum of the individual branch currents have to equal the total current. So IT in this case is IT equals I1 plus I2. If I substitute in the values, now you don't have to put these back in amps because they're both in milliamps, right? We did all that stuff in chapter 1, going back and forth between SI and standard and things like that. Since they're both in milliamps, I can just simply add them, and the total current here is 54 milliamps. So hopefully we're getting down pat. We know how to find the total resistance when we solve a parallel circuit now, that it is nothing like solving for total resistance in a series circuit. Ohm's law still holds true. All right, the relationship between current, voltage, and resistance. And then current, we had to use Ohm's law to do it, but what we learned is Kirchhoff's, however you say it again, right? His current law, the sum of the branch currents have to equal the total current. Make sure you got all this in your notes, all right? It'll come in handy when you show up to take the lecture quiz. All right. Another way we can find total current is if we know the total voltage and the total resistance. All right, we know the total voltage is 12 volts. We calculated the total resistance. It's 222 ohms. So I could take 12 and divide it by 222, and I should still approximately get 54 milliamps. Okay, so there's another way of getting the total current using the total resistance and using the total voltage or the voltage source to do that. All right, so a couple different methods there. You know, pick the one that's easier for you. Now we're going to take that same circuit. Okay, we just solved that circuit for total current, the branch currents, and total resistance. Now we're going to calculate power. Remember, calculating power, we have to use Watt's law. There's 3 versions of them. Power equals VI, power equals I squared R, or power equals V squared over R. We have all those components. We just calculated those in the previous slide. All right. We have RT, we have the individual currents, we have the total current, we have everything we need to find power. We just need to apply Watt's law. So make sure that's in your notes, that you have those 3 versions of Watt's law down. All right. So if we want to find the power in resistor 1, I'm going to use V squared over R1. Why? I know the voltage is 12 volts. It's a parallel circuit, and I know the resistance is 680. I don't have to mess with the current, okay? Maybe I gave you this and didn't ask you to find the currents. I've given you the voltage in the resistor. Use it to find power. All right, it's already given. So maybe you screw up calculating total resistance, but you can get the power calculations right on the test. You still get more points, all right? So we're going to take the voltage source squared divided by 680, because that's the value of R1. So it's going to be 12 squared divided by 680, or 144 divided by 680. You're going to get 0.211 watts, or 211 milliwatts. Okay? Or, all right, say you wanted to use the I squared R version of power. That's completely fine. All right? We know what I1 is. We calculated it before. Just make sure that you use it in its standard form. So you got to use 0.0176, okay, square it, and then multiply it by 680. So when you do that, you still get 211 milliwatts. So I'm showing you both ways to apply Watt's law there. You only do the one that suffices for you or what you're given. All right, let's find I2, the power through R2, I'm sorry, power through R2. Okay, using the voltage method, right? It's still 12 volts. It's a parallel circuit, and we just use R2. So 12 squared divided by 330. All right, you're going to get 0.436 watts, or 436 milliwatts. Or, say we wanted to use the other method. We liked I squared R better because we forgot V squared over R. All right, same concept. All right, we're using, just remember that you got to use 0.03636 when you do the calculation. times R3, which is 330, and you will still get 436 milliwatts. Now, how do we get total power? Well, kind of like getting total current, right? The sum of the individual powers equal the total power. This is the part that's the same for series and for parallel, okay? I can find the power absorbed in each resistor and then add them up. This is the only part where series and parallel are the same. So my total power is going to be the power through resistor 1 plus the power through resistor 2. So I got to take 211 milliamps plus 436 milliamps, all right, and I get 647 milliamps. So there's how we calculate total power. So now you've done everything you need to know how to solve for parallel resistance, solve for branch currents, and solve for power absorbed by each resistor. Once we get these down, series is good separately, parallel is good separately. We put them together, it gets a little scary, but we'll be all right. One other special case for total resistance is, say we have 12 resistors that are all 100 ohms. This is a shortcut in parallel resistance. I hate showing shortcuts because you try to apply them to everything, but this is a shortcut. If all the resistors in parallel have the same value, then you can take the value of that resistor and divide it by how many you have. So we got a circuit, it's got 12 resistors that are all 100 ohms of resistance. I can take 100 ohms and divide it by 12 and know that the total resistance will be 8.33 ohms for each branch. Please, please, please remember, this only works when all the resistors in parallel are the same value. Here's what I want you to do now. All right, we've already done this circuit with R1 and R2. I'm throwing a third resistor on there. I want you to pause this. Wait till I'm done talking before you pause it. And complete the table. I want you to be able to solve this entire circuit on your own. So take some time, get a separate piece of paper, look back at your notes, look at what we've done. Okay. Note the branch, you cannot use the same currents that we used before or anything for our I1 and R1 because the voltage is different here. The voltage in this circuit is 5 volts. We did one with 12 volts. So this is totally different, but I want you to go step by step. We've already calculated the total resistance, all right? That's given to you in the table. But I want you to figure out all the different currents, the total current, find out what's V1, V2, V3. Hint, it's a parallel circuit. You should already know those. And then calculate the individual powers and the total power. So what I'm going to do is I will fill in the table for you, and then on the next slide I will show all the work. I'm not going to go through it. I'm just, because it gets old listening to me say the same thing over and over. But on the next slide we'll have all the work for this. And I do expect you to be able to solve these on the test and on your quiz and on your lecture quizzes. Okay, it'll be on your midterm and your final. So make sure that you really know how to do this. If you have questions, email me, or I will go over another example or something with you in class if you guys need to. So remember, the next slide, I'm still going to talk a little bit after that, but the next slide will have all these step-by-step calculations for solving this. But I want you to give it a shot on your own. Fill in this table, draw the circuit out, solve all the missing parts. So I'm going to start putting the answers, so go ahead and pause the video right now and work through it. Alright, so if we look, remember it's a parallel circuit, so all the voltage drops should be the same. 5 volts, 5 volts, 5 volts. Alright, here's all the solutions to everything, and then here will be all the work. So just know it's a parallel circuit. V1 equals V2 equals V3. They all equal 5 volts. Alright, so you can do all your calculations. We already learned that all we're doing is applying Ohm's law at each resistor. We're using the total voltage or the voltage source, which is 5 volts, and dividing it by each resistor. So you should be able to get all those currents. And remember, the total current is adding up all the individual branch currents. So that's where the 13 milliamps came from. Then to calculate power, I just chose using the currents since we found the currents. You could still take the V squared over each R and find the power as well. It'll be the same thing, and then add up all the individual powers, and you're going to get 64.9 milliwatts. So, like I said, I think you guys should be able to get this by now, but if not, let me know. Work through some more circuits. You have some on your homework that you have to do as well. So please always don't hesitate to ask. I know it's a little different. We're doing all the lectures and everything online now so that we can do more hands-on in class as well. So it's kind of advantageous to you guys both ways here. All right, we already talked a little bit briefly about this. I just want to revisit it though. Kirchhoff's current law, right? The sum of the currents entering a node is equal to the sum of currents leaving the node. All right, it's really just what we talked about. Kirchhoff's current law is the sum of the individual currents have to equal the total current. So if you take 7.4 plus 3.3 plus 2.3, you should get 13 milliamps. Okay. Last thing we're going to talk about is current dividers. All right. I'm not going to spend a ton of time on current dividers. It's a way that you can find current in a parallel circuit if you need to, if you can't apply Ohm's law. Voltage dividers we use a lot more than current dividers, but same kind of concept. All right, don't get it confused with the voltage divider though, because it's similar, only it's kind of flipped. Remember, a voltage divider, we took a specific resistor over the total resistance times the voltage source. So if you look back at chapter 4 where we used voltage dividers, all right, and that gave us different voltage drops across the resistors. In here, it's going to give us the individual currents. What you really need to pay attention to is it will always be the opposite resistor over the sum of the two resistors. So if I want to find the current through R1, which is I1, I'm going to put R2 on top of the sum. If I want to find the current through I2, I'm going to put R1 on top of the sum. So it's the opposite. And notice instead of multiplying by a voltage source, we have to multiply by the total current. Okay? So there's how you use a current divider. Know which ones like swap and that sort of thing. I'm not going to force you to use a current divider. I might maybe put one problem for you to kind of look through and do. But just pay attention to the subscripts and what's where. Notice they are opposite. This is the best way to remember this. Best way to remember this formula. Okay? So let's take a look at one. We want to assume that R1 is a 2.2 kilo ohm resistor, and it's in parallel with R2, which is a 4.7 kilo ohm resistor. And I give you the total current is 8 milliamps. What's the current for each resistor? So if we find I1 first, it's going to be R1 divided by R1 plus R2 times IT. So 4.7 divided by 6.9. 6.9 is 2.2 plus 4.7. All right. So 4.7 divided by 6.9 times 8 milliamps. Remember, 8 milliamps is 0.008. All right. And we should be able to get that current through I1 is 5.45 milliamps. Why don't you guys pause and try and find I2 real quick. See if you can do that. And then I'm going to walk through it right here. So I2 is going to be R1 over R1 plus R2 times the total current. So it's going to be 2.2 divided by 6.9 times 8 milliamps. And if you plug all that in, you should get 2.55 milliamps. And to check yourself, all right, we know the total current is 8 milliamps. So 5.45 plus 2.55 should equate to 8 milliamps. So what do you need to notice though? The larger resistor has the smaller current. That should make sense, right? Because using Ohm's law in the relationship, voltage remains the same, right? Voltage is held constant. If resistance goes up, meaning we have a larger resistor, we should have a smaller amount of current. So that one should make sense, all right? Sorry, over-clicked there. Last one, real-world example. The picture down there is obviously a car's rear window being defrosted, just so you have an idea of what we're talking about, that literally your rear defrost is just resistive wires that you're forcing current through, and as you're forcing current through them, they're giving off heat, and them dissipating heat is what defrosts your window. Okay? So let's just work through this. It says assume there's 8 resistive wires that form a rear window defroster for an automobile. If the defroster dissipates 90 watts when connected to a 12-volt source, what power is dissipated by each resistive wire? So we're working backwards with power. And then part B says what's the total resistance of the defroster? All right. I'm giving you power now, and I'm giving you voltage. In your mind, you should choose Watt's law that involves voltage, power, and a resistor. That's what you should be thinking of, okay? That's what? P equals V squared over R. But we're solving for R now, okay? We're solving for R. So you have to rework Watt's law just a little bit to solve for it. So P, all right, so P equals what? V squared over R, where R equals what? The V squared over P. But in this case, we have to do some division first, okay? So what we need to do is what's going to be dissipated in each wire. There's 90 watts total in 8 wires. So we're going to take what? 90 divided by 8. So each wire is 11.25 watts. All right, so make sure we do that step first. Now we apply the Watt's law. We can just switch the P and the R. I mean, they're interchangeable for solving it algebraically. Remember, Watt's law is P equals V squared over R, but we need to solve for R because we're given V and P now. So we're going to get 12.6 squared divided by 90. So the total resistance in one wire is 1.76 ohms. 1.76 ohms. Okay, very small resistance. Why are we doing that? Because we want the wire to heat up. We want the wire to heat up to defrost the window, if that makes sense. All right, so that's just wires heating up. So what's the resistance? Okay, is if we take 1.76 times 8 ohms, or times 8, it's 14.1. Okay. So what I want you guys to do is at the end of the chapter in the book, just like we've been doing, are all the key terms. Please make sure that you study and know all the key terms and definitions. They're at the end of the chapter. I would write them all down if I were you. You can always pause the slide or the video and go through them. And hopefully you got a stronger sense of parallel circuits now. Hopefully you're doing all right with series circuits, because in chapter 6, we're going to take series circuits, parallel circuits, and combine them into one, and we're going to get a series parallel combination circuit, or combo circuits. Okay? So with this, all right, please feel free to email me, or when you see me in lab, ask me any questions if you need me to work through a problem. All right, I'm more than happy to.